So these are our notes on intermolecular forces. So if you haven't opened up your Cornell template, go to Classroom, click on Classwork, Unit 6, and then you want to find the intermolecular forces note and open up your document. Once you're done, you want to make sure that you add highlights and a 3 to 5 sentence summary, and then create a link to your completed notes on page 28 before turning them in here on this assignment. All right, so let's go ahead and get started. All right, so intermolecular forces, okay? So there's 3 of them that we're really going to focus on. Intermolecular, just to start off, inter means between molecules, kind of like interstate, right? Interstate highways are between states. These are between molecules, okay? All right. So our essential question here is, what are the 3 intermolecular forces and how do they affect compounds? Okay. All right, so talking about intermolecular forces, there are forces holding atoms together in a molecule. So you have one hydrogen chloride molecule here and one here. And there's a force between the chlorine and the hydrogen that actually holds them together. The covalent bond, of course, is the strong intra, which is within the molecule, molecular attraction here, where you can talk about that's that covalent bond. These are weaker than the actual bonds themselves that we just talked about, okay? So forces holding atoms together in a molecule is intramolecular. And so those examples, of course, are ionic bonds and covalent bonds. And, of course, those are those electrostatic force holds them together. But the intermolecular, which we're going to talk about, like the interstate between them, is what we're going to focus on here. We've focused on these already. Now we're going to focus on what happens here. So these are the attractions between molecules, and they are weaker than the intramolecular forces, okay? These intermolecular, these weak ones here, attractions are strong enough to control physical properties. So we're going to talk about how they affect that, such as boiling point, melting points, vapor pressures, which is just how much pressure you have to add to turn it into a gas, and then viscosities. And viscosities just means how it pours. So like honey has a higher viscosity than water because it really sticks together, okay? The 3 forces, we're going to talk about the intermolecular ones. They can also be called van der Waals forces. And the 3 we're going to focus on is dipole-dipole interactions, hydrogen bonding, and London dispersion forces. Okay, a couple definitions before we get started. A dipole is a molecule in which one end is positive and the other is negative. So di means 2. Poles means 2 poles. So there's a positive side and a negative side. Volatility, if you hear me say that, that is a tendency for a substance to evaporate. So it's how fast. So if it has a high volatility, it will evaporate. It has a very low boiling point, so it evaporates very fast. And you'll see in the lab some things that have a very low or high volatility. Okay, and which means it has a low boiling point. Solubility means the ability for a molecule to be dissolved in water, so it's soluble. Okay. The first one we're going to talk about is the London dispersion forces. And London dispersion forces are attractions between an instantaneous dipole. So they change. So what happens is, remember we talked about metallic bonds, how those electrons move around. Well, that's what happens here. It's almost like the electrons move to one side and then they all move to the other side. And so that kind of changes where the pole is. So you can see here, if the electrons are all on this left side, then you get kind of a negative on this side and a positive over here because the nucleus is over here. And then same thing here, okay? And this one, when all the electrons are on this side, pulls that nucleus a little bit closer. So that holds them weakly together. But the funny thing about London dispersion forces is that they disappear. So while the electrons in the 1s orbital of helium would usually repel each other, sometimes they end up on the same side. So you think they would end up on very inside opposite sides because they're electrons. They don't like each other, but sometimes they end up on the same sides, causing that what we call that dipole, one negative side, one positive side, okay? And then the electrons on the same side of the atom causes it to have poles, okay, just like you see here, a positive side and a negative side. So the electrons are here, the proton is over here. An excess of electrons on the left side gives us a slight negative, and a shortage on the right gives us a slight positive, okay? And the poles would cause another nearby helium molecule to have poles as well. So basically what would happen is, because these are negative here, push those electrons that way, so then it can attract this positive. Then the two helium molecules would then be attract to each other and kind of just hold on, kind of like a loose handshake, okay? But what can happen in London dispersion, also remember, is those electrons are always moving, so they can move to the other side. So that's why we call them dispersion, because they just kind of disperse randomly and then come back. The other one that we'll talk about is a dipole-to-dipole interaction. And these molecules that have permanent dipoles. So we just talked about London dispersion, where the dipoles can show up and then they go away. And then they show up and they go away. But in a dipole-dipole, it actually stays, and it's a permanent one. Those don't move around. Okay, so when does that happen? So the positive end of one is attracted to the negative end of the other. So you can see here is a molecule here, and it's of cyanide here. And so then you will have a positive end and a negative end, okay? And they will stay that way. So this one with these two white ones will always be positive. The one with the blue one will always be negative. So this one is now attracted to the white end of this molecule. This white one is attracted to the blue end, and these never change. So they stay that way, okay? And this is when you really see something stay either in a solid or a liquid, and it's really hard to get it into a gas. And water has this as well. Water has a very positive and a very negative end, and that's why water sticks together and you see surface tension, okay? And then also, the more what we call polar, the more positive or negative it is, the higher the boiling point. So you can see propane is here. The boiling point is 231 Kelvin. Dimethyl ether has a slightly higher, and then acetone has a slightly higher, and acetone nitrile has even a higher. Okay, and water, that's why water also has a higher one, higher boiling point than usual, and that's because it does have this dipole to dipole. The last one we'll talk about is hydrogen bonding. Hydrogen bonding is the dipole-dipole interaction experience, but it's only when hydrogen bonded to nitrogen, oxygen, or fluorine. Okay, this is something that happens in your body all the time, and we call these interactions hydrogen bonds. So you can see oxygen to hydrogen. There's a hydrogen here. This is water. There's a hydrogen bond here. This, of course, is the covalent bond. This is that intermolecular hydrogen bond. So that's why water sticks together. Hydrogen fluoride, ammonium, okay, all kind of stick together and stay. And these are all very organic chemicals, and so that's why they all stick together, because not only do they have the hydrogen bonds, but also you just heard me talk about water has also a dipole to dipole, and then most all molecules will have that London dispersion. The electrons move from one side to the other. It's kind of like a teeter-totter, but water is one of the things we'll deal with a lot because it actually has all three. And so hydrogen bond rises in part from the high electronegativity of nitrogen, oxygen, fluorine. These are all very far to the right of our periodic table. So they have a high electronegativity, so they will pull those electrons as much as they can, and that's what causes that positive, negative, really high side, which pulls the other molecules towards them. Also, when hydrogen is bonded to one of those very electronegative elements, the hydrogen nucleus is exposed, which gives us that if the nucleus is exposed, of course, those are our protons. That's where our nice positive side sees. And you'll see in the lab how water, I can actually repel it, or you can attract it with different things. Okay. Intermolecular forces affect many physical properties. So the first thing is it affects boiling points, and you'll see that in the lab. The melting points, volatility, surface tension, and solubility of a molecule. And in the lab, I will actually show you a volatility one, surface tension, and then I'll also show you attraction with water. The more intermolecular forces a compound has, the higher the boiling point, melting points, and surface tension. So you'll see when we do the volatility, I will do water with a couple other ones, and you will see that because water has all three of these, it has a very low volatility, which means, or high volatility, which means that it evaporates, a low volatility. It evaporates very slow compared to some other ones, okay? All right, strength of intermolecular forces. The strongest intermolecular force we've talked about is hydrogen bonding. Dipole to dipole is the next because this is a permanent thing. Dispersion is the least because it changes. It disperses, it goes away. All right, so now go back to your notes. I want you to process your notes, highlight any important notes, make connections to any of your notes in the left-hand column. Write any questions you may have in the left-hand column. Use your highlights, connections, and questions for your summary, and then write a 3 to 5 sentence summary. If you guys have any questions about this, please let me know.